Welcome to the 6th lecture of optical sensors course. In the last lecture, we discussed the propagation of an electromagnetic wave at an interface, and we solved for the reflection and transmission coefficients for a p polarized wave. P polarized means TM polarized wave, where the electric and electric field components are in the plane of incidence. And I gave a homework for the waves which have electric field component perpendicular to the plane of incidence. So, I hope that you have solved for the reflection and transmission coefficients for that. Now, we move ahead and we discuss certain properties associated with this and want to see what happens to it. So, let us see the reflection coefficient was n1 cos theta 2 minus n2 cos theta 1 divided by n1 cos theta 2 plus n2 cos theta 1. This was the reflection coefficient, and the transmission coefficient Tp was equal to 2 n1 cos theta 1 divided by n1 cos theta 2 plus n2 cos theta 1. So, we have these two. Now, if you saw the energy conservation, according to energy conservation, all the EI0 square plus mod ET0 square should be equal to ER0, must be equal to ET0 EI0 square, right, which means that or P square plus Tp square is equal to 1. Let us try to solve it. So, it becomes like n1 cos theta 2 minus n2 cos theta 1 divided by n1 cos theta 2 plus square plus n1 cos theta 1 n1 cos theta 2 plus n2 cos theta 1, this all square. So, what do you get? You will get, so this will be, the denominator is the same. So, you can have n1 cos theta 2 minus n2 cos theta 1 divided by n1 cos theta 2 plus 2 cos theta 1 whole square plus 2 n1 cos theta 2 divided by cos theta 2 plus n2 cos theta 1 square. So, we can see that it is in the denominator you have n1 cos theta 2 plus n2 cos theta 1 whole square, and here you have n1 cos theta 2 square plus n2 cos theta 1 square minus 2 n1 n2 cos theta 1 cos theta 2 plus 4 n1 square cos square theta 2. So, numerator you can see that is not equal to n1 cos theta 2 plus n2 cos theta 1 square, because you have this a square term, b square term, but you do not have plus 2ab term. So, this is not equal to this. Hence, numerator divided by denominator is not equal to 1. You see that this does not come equal to 1. So, where are we wrong? I mean there should be something wrong with it. It does not come 1. So, what is problem? Why are we not getting this? So, something is wrong here. The energy of an electromagnetic wave is given by the Poynting vector. So, we have to solve for the Poynting vector. So, let us solve for the Poynting vector. So, the Poynting vector S was given by E cross H, and we can write it 1 by, and H was given by 1 upon omega mu naught K cross E, and E is equal to E 0 e to power I omega t minus k dot r. We know this. So, this can be written as 1 upon omega mu 0 k cross E 0 into e to power I omega t minus k dot r, right. What does it give? So, if we want to calculate H S, that is E cross H, that is equal to half of real of E cross H star. You can solve it for this, and that is 1 upon 2 omega mu 0 E 0 cross k cross E 0 star, and that is 1 upon 2 omega mu 0 mod E 0 square into k minus 0. So, you know this identity, I told you about this identity, A cross B cross C was equal to B A C minus C A B. So, use this identity, I told you on that day to prove it. So, go back and prove it and try to see what happens. So, we end up with this relation. So, that is S is equal to 1 upon 2 omega mu 0 mod E square k. So, S gives the direction of flow of energy. So, this is the so we solve for it and we go to see what happens. So, this is our interface, a beam is coming like this, it is getting reflected from here, and this is the area. So, this is was x direction, if you remember, this is z direction, this is S now flowing in this direction, and this is dA, it is the area where it is falling, that is dA into x. So, energy entering in the area dA per unit time SI dot dA. Similarly, energy reflected from area dA per unit time SR dot dA. So, this is area. Energy transmitted from area dA per unit time is ST dot dA. So, in principle S I dot d A should be equal to S T dot d A plus S R dot d A, that is mod E I 0 square K 1 is equal to into d A is equal to mod E R 0 square into K 2 it is also K 1, no, this one is K 2 dot d A R T actually plus mod E R 0 square dot K 1 dot d A. So, K is small actually, sometimes I write it seems like capital, but it is small k. So, you have actually mod E I 0 square into K 1, K 1 is actually omega by c into n 1, omega by c into n 1 cos theta 1, you take the theta component is equal to mod E R 0 square omega by c again n 1 cos theta 1 plus mod E T 0 square omega by c now n 2 cos theta 2. So, because it was a vector I now that is why you have cos theta 2 and I have removed dA now. Okay. So, we arrive to this relation, omega by c cancels out from here. Now, you have mod E I 0 square is equal to mod E R 0 square plus n 2 cos theta 2 divided by n 1 cos theta 1 into mod E T 0 square. This is the equation which needs to be satisfied. For energy conservation. If you simply want to say that mod rp square and mod tp square is equal to 1, that is wrong interpretation. You must have it in terms of the Poynting vector, because that is the vector which gives you the energy flow, and from here we arrive to this relation which gives you the actual equation which must be satisfied to prove the energy conservation. So, from here if you want to calculate what are the Rp is equal to simply mod Rp square, and that is equal to E R 0 square divided by E I O square, and Tp is equal to which is mod E T 0 which is E T 0 square divided by E I 0 square is equal to into n 2 cos theta 2 divided by n 1 cos theta 1. This is something, and this is n 1 cos theta 2 divided by n 2 cos theta 2 divided by n 1 cos theta 1 into Tp. So, this is the correction. So, it is not like that Tp is equal to small mod Tp square is not equal to Tp, you have to have this coefficient also. So, now we have arrived here and we know that energy these are called energy reflection and transmission coefficients, You want to have total energy, you have to sum of it. Okay. So, now we know that if a wave, electromagnetic wave is incident at an interface of two media, it will at an oblique incidence, that its reflection and transmission is governed by this Fresnel equations, and from there you can calculate the amplitude of the reflected and transmitted wave. And from all this exercise which we have done, you can arrive to the condition where you can calculate the energy transmission and reflection coefficients. And let us see what happens at certain special cases when this reflection and transmission goes 0. So, we know that R p is equal to n 1 cos theta 2 minus n 2 cos theta 1 divided by n 1 cos theta 2 plus n 2 cos theta 1. If numerator is equal to 0, then R p is equal to 0. What does it mean? It means that for p polarized light means the electric field component which is so an electric field component which is basically electric field component which is in the plane of the incident light will not be transmitted. So, there will not be any reflection of this electric field. So, let us see what happens. So, n 1 cos theta 2 minus n 2 cos theta 1 becomes equal to 0. This means n 1 cos theta 2 is equal to n 2 cos theta 1. This is one condition. From Snell's law, we know that n 1 sin theta 1 is equal to n 2 sin theta 2. We know that n 1 sin theta 1 is equal to n 2 sin theta 2. So, if we divide this from equation 1 to equation 2, what will happen? So, let us say that if we divide it, then what will we get? So, n 1 sin, again I am writing that n 1 sin theta 1 is equal to n 2 sin theta 2, and you have n 1 cos theta 2 equal to n 2 cos theta 1. So, you can have it like this is suppose equation 1, this is equation 2. So, you can have n 1 n 2 sin theta 1 cos theta 2 is equal to n 1 n 2 sin theta 2 cos theta 2. So, n 1 n 2 and cancels out, you have sin 2 theta sin 2 theta 1 is equal to sin 2 theta 2. When is this possible? This implies that 2 theta 1 is equal to pi minus 2 theta 2. To satisfy this, this implies that theta 1 plus theta 2 is equal to pi by 2. What does it mean? It means that this angle theta 2 when light was incident, theta 1 plus theta 2 should be 90 degree. So, if you have this wave which is travelling, and if you have theta 1, you have theta 2, then you have all the light like this which is coming here, it goes, all the light gets transmitted, no light gets reflected. So, if it is theta 1, so basically this angle should be 90 degree, this angle should be 90 degree. So, theta 1 plus theta 2 is equal to pi by 2. So, if you have n 1 sin theta 1 is equal to n 2 sin pi by 2 minus theta 1, then that means equal to n 2 cos theta 1. So, it becomes like sin theta 1 by cos theta 1 is equal to n 2 by n 1. This implies that tan theta 1 is equal to n 2 by n 1. This tan theta, this theta is called Brewster angle. So, this is called theta 1 is Brewster angle when theta 1 plus theta 2 is equal to 90 degree and RP is equal to 0. So, when RP is equal to 0, it satisfies this condition. This is Brewster's condition, and it is called Brewster angle. So, what happens at Brewster angle? RP goes to is equal to 0, and you see that we can have this ray like this. You have electric field components in the plane and electric field components out of the plane. So, these ones components perpendicular to the page and components parallel to the page. So, this one is parallel to the page, this is called P polarization, this is called S polarization or TE, and this is TM, transverse magnetic. So, you see that at the when the angle of incidence, when theta 1 is equal to theta b, the Brewster angle, all the P polarized light gets transmitted, it does not get reflected, only S polarization gets reflected, and this was the condition we derived, and it was equal to 90 degree. So, why it happens so? What is the reason behind this kind of transmission, like complete transmission of light at Brewster angle? If you have P polarized light, then all the light goes into the transmitted medium, does not go into the does not reflect back into the same medium, and this happens only when this angle is 90 degree, means theta b plus theta 2, theta 1 plus theta 2 is equal to 90 degree. We knew that. So, if this is 90 degree, this is totally 180 degree from here to here. So, this is 90 degree. What is the reason? So, here is the physics. You know that when light is incident on any medium, I told you that how it propagates. So, when light gets transmitted through a medium, what happens actually that it excites dipoles, and the dipole oscillations we discussed that power was dp by d omega was proportional to sine square theta by lambda to the power 4, where this theta was the angle made from the axis of the dipole. So, if this was the axis of the dipole and you want to measure here at an angle theta, and this was the solid angle, if you remember, d omega, and we wanted to see how much power it is here, it was making from the axis actually axis. So, at theta is equal to 0, there is no power radiated. So, all the light and the maximum radiation goes in 90 degree to the dipole oscillations. So, if it is incident in such a way that reflected ray and transmitted refracted ray, this make 90 degree angle, that means that the dipole is oscillating in such a way that it does not produce any radiation in this direction. So, all the light comes in that direction, that is the basic physics behind this. So, our oscillating dipole does not emit along its axis, all the light is going, that is why into that direction. So, this is something very important, this is very small very basic concept, and most of the people forget, I also sometimes forgot about this. So, how does it look like when you have an interface, say from n1 to n2 light is going like this, and you increase the angle theta, you keep on increasing the angle, what will happen? And you want to measure the reflected light. That is how you perform the experiment for Brewster angle. So, this is also theta 1, this is also theta 1. So, what happens actually that when you start from 0 degree of angle of incidence around for this particular condition, when you have n1 is equal to 1 and n2 is equal to 2, the reflection coefficients, energy reflection coefficient Rs and Rp has been plotted here, and you can see that Rs goes like this blue curve, while Rp shows a dip here, and this is because of the Brewster angle. So, at the Brewster angle theta b, all the light gets transmitted and the reflection is 0. So, can we do sensing using Brewster angle? Why? How do I say that? If you remember that when we were discussing sensors, it was shown that it has certain characteristic. Here I have theta, and here I have reflection and reflected power, and I want to see what happens. Say suppose this is condition for n1 n2. Now you choose another, I just change from n1 to n3, n2 to n3. Does it shift? Can I measure the shift? So, the basic idea behind that is, can we use it for sensing applications? That the basic question, and answer is yes, we can use it. So, tan theta b was given by ns by na. Now, I have put it, ns is actually n2 and this is n1, and now why I write a and s is like s is for substrate and a is for analyte. That is how write. Analyte is the medium which we are trying to sense. So, I have already a substrate, I put suppose I have glass slide, I put a drop of water, I want to see the Brewster angle. So, if you have this relation, we know that if we are measuring theta in terms of Na as a function of Na, then d theta by dNa will be the sensitivity. You want to calculate the sensitivity. So, we can use it for sensing, as I told you here, that if we move from n2 to n3, this Brewster angle theta b1 will be theta b2. So, it can be done in principle. Can we, but if it works as a sensor, what will be its sensitivity? That is the question. So, what you do is that you take the derivative of this, and derivative is given by this relation. You know that d tan x by dx is equal to 1 by cos square x, that is sec square x. So, you can write d tan theta by dNa into 1 upon cos square theta b d theta by dNa. So, you arrive to this relation, somehow these have changed, actually this has to be theta b, and what we see is that we get this relation ultimately, that it is the sensitivity depends on only on the refractive indices of ns and na. So, for an example, to take an example, we have put water on silicon substrate, and you know that the sensitivity is around degrees per refractive index unit, which is very small, very small. I will show you that the sensors have very high sensitivity, very high sensitivity. So, this is very poor sensitivity. Also, there is a problem with the large width of the curve. So, I told you that if there is a very small change, suppose this curve is like this and then you have another curve which is like this. So, it is very difficult to find what is the change in the curve parameter due to shift in the refractive index. So, it has very small figure of merit. I hope that you remember how you define figure of merit. That was sensitivity versus divided by delta. Here it will be delta theta. So, if the delta theta means like FWHM. So, theta FWHM is broad, that means the figure of merit will be poor. If we want to use it other way around, like we were putting on a substrate, we were putting a drop and we were shining from here. So, here was the analyte, which you do not prefer most of the time. So, can we put light from here and see what happens and measure the reflectivity here. So, that can be attained by using a prism. So, the analyte is from the other side and you shine from the prism side, light goes here, gets reflected from here, and here is your analyte. So, you arrive to the same equation, only there is a minus sign in the previous one. So, the sensitivity is the same. So, it does not make any difference. Brewster angle for the air water interface is about 53 degree, 53.5 degrees, at which maximum polarization in reflection occurs. So, you can see that when the angle is large, say during the morning or evening times, you have maximum polarization in reflection. So, sometimes you do not see even reflections, because if you see only if you are using a p polarized light. Similarly, what it can be shown here, that when you are measuring, when you are looking at a grazing angle, at an angle about oblique angle about 53 degrees or so, you see only small reflections coming from. So, that is used basically in photography, that if you want to avoid speckle, you use this kind of filters at this particular angle. Water beetles, bugs and birds use this fact to detect bodies near the water surface, and you can cut down the glare from reflections at Brewster angle. So, we studied polarization by reflection at Brewster angle, and the potential use and limitations of Brewster angle for sensing applications were presented. Thank you.